So let me explain that a little more, the Runge-Kutta method, and let me explain that a little more in detail, what I mean, right? So essentially, so we've got this equation now, right? So our equation is basically this, okay? So right? So the way we progress here, right, is in our equations is this. So I'm going to just write it like this, okay? This is my equation. So I'm going to just say that let this y1, okay, be equal to f, right? Let this be f, then dy1 d eta is equal to f dash, right? And let's call that as y2, okay? And that is this, okay? Then dy2 d eta is nothing but f double dash, and let's call that as y3, okay? And dy3 d eta is nothing but f triple dash, which we get from this equation, if you see, to be equal to f double dash, which is equal to y1 into y. So it is y1 into f double dash, which is y3, y1 into y3. So this is essentially, what I get, I mean, how I kind of start out, okay? Then, so this is what I'm going to actually look at, okay? See how we will develop the Runge-Kutta method, okay? So now, again, let us look at the boundary conditions as well. Let's look at the boundary conditions. Now, at eta is equal to 0, right, which is, that is basically at the wall, okay, at the wall. So f is equal to 0, right, which means the function itself is 0, so say y1 is 0. So this y1, y2, y3, these are your variables which I'm using in the computer code. So I'm kind of writing it that way. So y1 is equal to 0, okay, and f dash is also equal to 0, which is y2 is also equal to 0, okay, and f double dash, which is y3, okay. So y3, okay, this is equal to some value. So it is some, we assume some kind of value, so which is equal to a, right. This is an assumed value, so you assume whatever you want, okay. So because this is we kind of assume a value, we start with an assumption and then we iterate on this, okay. And at eta far away from the wall, right. So in this case, when I say far away, so eta could be 10, right. I think I spoke about that. So then f dash, okay, which is equal to y2, okay, is equal to 1. So this is essentially my boundary condition, right. So this thing, and then I've called it, eta infinity in my code, this one, y2 underscore inf, okay. So you can sort of see that, that's the name of the variable. So that's how you put it in the code, okay. And all of these things are input. So okay, let me just sort of speak about that a little bit, how we sort of input that into the code. Now, the interesting thing is that, say this is your boundary layer. Okay, now this is your y, this is your x, right? And say This is your boundary layer. Okay. Now, what we will basically do here is at a particular section, right, if we go like that. And we take, what we do is, I'm going to go like this, we take several sections like this, okay, and so on and so forth. So, essentially when I come, so say, let us say, so this section, okay, let me call that as, so yeah, so this is say section 1. You know, in a computer code you can't start from 0, so you start from 1. So, the section, so this point rather, the location, right. So, this is say at some location x, isn't it. So, now at this point, okay, say this is 1, this is 2, this is 3, 4, 5, 6, blah, 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 7, 8, 9, 10. Okay. So, we will sort of do this. Now, so in order to do this, so let us say this is, you know, at any point, right. So, let us call this as say I. So, then you can write that as I plus 1, I plus 2 and so on and so forth, right. So, then I can say that this I is basically an index which goes between these sections. Now, this is essentially my you know, the height which basically I decide. Okay. So, I decide that, and that I am going to call as h, right. I am going to just call this as h. That is really up to you, you know, how small you want it to be. Okay. So, I do this. Now, so then therefore, I can say that this I basically loops from say 1 to 10, right, because we said that from very far up. So, what we are going to do with 8, 9, say 10, right. That should be probably okay. So, you can go further and check and see, you know, what is a good thing for you to do. And what we have right now, so therefore, so if I have something like this, now for example, let us say I be at the wall. What I am going to do here is sort of just zoom into this zone, right. So, what I have here is therefore, I am zooming into this section. So, this section is I, and this section is I plus 1, right, and this section is my wall also. This section is also my wall, right. So, if that is so, right, so then the boundary conditions that eta is, so here eta is 0, y1 is basically 0. So, what I am going to say, so the way I write that in the computer code is I say y1, this becomes an array, right, this is 1, right, is equal to 0, because like I said, the I is equal to 1, right, here in this particular case is 0, right. Again, y2 is 0 and y3 is something. So, so y2 again, y2 at 1 is equal to 0, okay, and y3 right. So, y3 at 1 is equal to this value a, right. So, the way I have written it there is that I basically call it y3 at the wall. So, that is something I define, you know, at the beginning. So, I define two values, and I call it y3 at the wall. So, that you do not have to go and change anything here all the time, this will be at the top, and y3 at far end. So, and I call that as infinity, right. So, this one is say some value, say I start with say 0.5, and this is equal to yeah, well, sorry, 1, right. So, therefore, I am going to write this as y3 wall, right. So, when you change that, all you do is just change here, do not touch the code. Okay. So, that is how we sort of do that. Okay. So, now what I am going to do is, again I am going to take this, now that I have I and I plus 1. Now, that here in this particular case, I basically am going from the wall, the I is at the wall, but this essentially you could take anywhere. So, if this could be I, this could be I plus 1, I mean it doesn't matter. So, anywhere, so I am taking this so that here we we'll be able to use these kind of boundary conditions only here, right? Okay, and oh sorry, and this one y2 at infinity, so you could just say, so like I said, you know, so this we can call this as, say, capital N, and this could be you know, also an input value. So then I write this boundary condition basically as y2 n is equal to y2 infinity, which also I have as this one here. Okay. So now let us come to this Runge-Kutta stuff. Okay. So, so this Runge-Kutta stuff, right. So I'm going to use basically, again, if I sort of zoom in, okay, I'm going to just zoom in here, okay, and this is, say, I, and this is, say, I plus 1, right. And like I had explained, so basically I will take 2 points, I'm going to integrate the value. So basically I'm going to integrate, you know, my equation. So you can see that I have these, you know, derivatives here. So I'm trying to integrate that between I and I plus 1, right, in this section whose height is h, right. I'm also going to estimate the location of these 2 points. Okay. So this is all within this height of h. So how do I do that? Okay. So how do I do that? Now the way I'm going to just write out the variables that I'm using in the computer code. So the first time I write, so basically I say, this is the name of the variable that I'm using. Okay, this is the name of the variable that I'm using. So like I said, so this is 0.1, okay, 2, 3, and 4. Okay, so then I say ky1, okay, 1 is equal to y2 I, right. What is y2? y2 is nothing but f dash. So what I'm saying is I am doing this variable which is ky1, okay. 1, this 1 is corresponding to the first point in the in this incremental length, okay, incremental height, let's put it that way. So this is the first location of the incremental height. So ky1, this value is equal to y2 at I, and y2 is nothing but f dash, right. Then ky2 at 1 is nothing but y3 again at I, right. So ky2 is another variable, and y3, what is y3? y3 is nothing but f double dash, right, f double dash. Then ky3 at 1 is nothing but minus y1 1, right, y1 I, right. So this is the syntax, this star is what is the syntax in what you will do. So basically I'm going to multiply this, or let's just say I'm going to do this, okay, y1 and y3 I, right. So what we've essentially done, so we got y2, right. So we got y2 and we got y3, and hence we calculated this term. So y1 and y3, okay, and this y1 and y3, from where do I get? It is nothing but this third equation, right. So we are writing out essentially so we are writing out 1, 2 and 3. So these are the equations that I've actually written out, if you see in the computer code. So ky1, right. So let's just say right. So if you see, let me go further down a little bit just to sort of, you know, give you just to show you that, okay. Right. So a little further probably, sorry about that. Okay. right? So if you see here, so essentially what I'm saying is, so these are the three equations, 1, so 1, 2 and 3, which is what I have written out here if you see. Okay, I think, and I missed the negative sign here, so let me sort of write that out. Well, that kind of, you know, depends. Sometimes you have, it depends on how you are defining your variable. Okay, you could or could not have, you know, the negative sign. You could also have a half. Some people also have a half. It really depends on how you're defining your, you know, variable, the variable. So in this particular case, my equation is really, I guess, you know, just yeah. So I do have like a negative sign here, right? So this is a negative sign. I kind of missed that. So it's equal to this. I do have a sign like that. So I'll probably have this equation here. Okay. So that's how my equation changes. Okay, so now, so essentially y2, this equation 1, 2 and 3 is what I have written out here if you see. So I'm going to, so basically I'm saying that ky1, you know, so ky1 is nothing but, so I'm writing this derivative as ky1, 1, which is at this location, and that is y2. Then ky21 is, I'm writing as y3, which is this, again at this location, ky3, which is this, and 3 is equal to minus y1, y3. Right. So this is something that I write at 1. Okay. Okay. So now let's go back. Then, right, then what we will do, so let me write it here. Okay. Then we are going to move to the next point, so which is 2. Now, so this is very interesting. So now all we do here is then we say ky1 at 2 is equal to, okay, y2 I, or you could write here this, or you could write ky1 1, which is like the value from earlier, you know, earlier step. So this plus 0.5 into delta eta, yeah, delta eta. So basically this is h, right, this h, so let me write that as h, okay, into ky2 1. So ky2 1 is already something that you've calculated here. So this is what it comes to. Then ky2 2 is y3, this thing, plus 0.5 into h, ky3 1. And ky3 is from here in the previous step, right? And then ky3 2, okay, is equal to essentially y1 I, right, plus 0.5 into h into, okay, into ky1 ky1 1, ky1 1, okay, ky1 1, right, into y3I plus 0.5 into h into ky3 1, ky3 1. Right, you get that. So then again, so once we have that, so then again we go back to 0.3. So you can see basically what I'm saying is that this is making an estimate at this point 2. This is the ky1, ky2, ky3 is essentially value here, right? So then ky1 at the point 3, which is here, is equal to, right, at the point 3. So it's so you have to use original values here. So again, y2 I, right, okay, plus 0.5 into h into ky2 2, right. So now it's just at the previous location. Then ky2 at third point is y3 plus 0.5 into h ky3 2, okay, and ky3 3 is equal to minus y1 I plus 0.5 into h into ky1 2, right, in this case 2 into y3 I plus 0.5 into h into ky3 2, right. So that's at the third point, and what do we have at the fourth point? So again ky1 at 4 is nothing but y2 I, right, plus so that is delta eta, okay, ky2 3, right. Let's just put a multiplication there. Then ky2 at this point is y3i plus h into ky3 at the previous point, and ky3 4 is minus, okay. So y1 I plus h into ky1 3, okay, into y3 I plus h into ky3 3, right. So now the moment you find this, so what you see is, so you get, so essentially, so now you've got some values here at I. How do you get the values at I1, right? Now we've got some ky's and stuff like that, so then what do we do now? So therefore we say that y1 at I plus 1 is equal to y1 at I, right, plus 1/6 of what, right, 1/6 of ky1 at 1 plus 2 ky2 at 1, right, plus 2 ky3 at 1 plus ky, okay, sorry, so yeah, ky2, ky1, yeah, actually, just a sec, ky1 at 1 and ky1, yeah, sorry. So this is, we will use ky1 everywhere, right? So this is ky1, okay, at 2, ky1 at 3, ky1 at 4, right, into the h, delta eta. So you get that. So then you get y2, right, I plus 1 is y2 I, right. So we get okay. So we get, sorry about that, and so this is y2 I plus 1/6 ky2 1 plus 2 k, okay, sorry about that, this is ky1, right, 2 ky2 2 plus 2 ky2 3 plus ky2 4 into h, and y3 I plus 1 is y3 I plus 1/6 ky3 1, 2, I keep missing a few things here and there, so this is ky2. So ky3, 2, 2 ky3, 3 plus ky3, 4 into h. So essentially what we are doing is the ky values at the first location. So this is at the, if you see the I location. So we get at the I location, or see this is at first location, this is the second location, this is the third location, and this is the fourth location, which is I plus 1, right. So this is the first location. Okay. So that's what we do. So for y1 we use ky1, for y2 we use ky2, for y3 we use ky3, and that's it. That's how we basically get, and we integrate from there to the top, and finally when we get to the top. So now the thing is, now that we do this, okay, now that we do this, we are writing all this, right, this I, right. So now you can put this entire thing in a loop, and you say that I goes from, say, 1 to this n, which we've defined, right. So then you loop this through, right, and you loop this entire through here. So say loop. Okay, I am just writing this. This is not how you would write the computer code. So okay, let's see. So basically, we will. So then you sort of loop this through, right? You loop this. So if you go from I to n, so you start from 1, and you will see that you will do this entire thing as you go from, right, as you go from each step. So you start out at the wall, and then you go towards the free stream, right, and then you use this boundary condition. So that's exactly what we do in terms of the Runge-Kutta. Okay.